We live with gravity 24/7. It's always there, keeping our feet on the ground, making sure our coffee stays in our mugs. But what is it really? Why does everything fall down instead of just floating away into space? Let's unpack one of the most important forces in the entire universe, and I promise we'll do it without frying your brain. For a very long time, people thought of gravity as some kind of mysterious, invisible pulling force. You've probably heard the story about Isaac Newton sitting under an apple tree. An apple falls, and instead of just eating it, Newton starts thinking. He asks the big question, why did it fall straight down? Why not sideways, or even upwards? This simple question led to a huge breakthrough. He realized that whatever force was pulling that apple down to the ground was the very same force that was keeping the moon locked in its orbit around the Earth. It was a revolutionary idea connecting everyday objects to the movements of the heavens. In Newton's view, every single object that has mass pulls on every other object. Think of it like a cosmic attraction. The more mass an object has, the stronger its gravitational pull, and the closer two objects are to each other, the stronger that pull becomes. This is why we feel the pull of the Earth so strongly. Earth is absolutely enormous, so it has a massive amount of the force you feel pinning you to your chair right now. That's what we call your weight. It's just the Earth's gravity pulling on your body's mass. So, bigger planet, stronger pull. That SYUD way less on the moon it. S much smaller and has less mass than Earth. Newton's idea was brilliant, and it works incredibly well for most things. It helps us launch satellites and predict the paths of planets. But for over 200 years, that was the best explanation we had. Then, at the beginning of the 20th century, another genius came along and changed everything. His name was Albert Einstein. He looked at gravity and presented an even deeper, more mind-bending idea. Einstein said that mass doesn't just pull on other things through some invisible force. He proposed that mass fundamentally changes the very fabric of the universe around it. It actually bends and warps something he called space-time. Okay, so what on earth is space-time? It sounds like something straight out of science fiction, but it's a real concept. Imagine space and time aren't separate things, but are woven together into a single four-dimensional fabric, kind of like a giant, stretchy trampoline. Now, picture placing a heavy bowling ball in the middle of that trampoline. What happens? It creates a dip, a curve in the fabric. According to Einstein, that's exactly what massive objects like planets and stars do to space-time. They bend it. So let's go back to that trampoline. If you roll a smaller marble near the bowling ball, what does it do? It doesn't roll in a straight line anymore. It follows the curve in the fabric created by the bowling ball. It might even start to circle around it. We see that motion, that curved path, and we call it gravity. So, an object in orbit isn't being pulled by an invisible rope. It's simply following the straightest possible path through a curved, warped region of space-time. It's just geometry on a cosmic scale. This completely changes how we think about the solar system. The planets in our solar system aren't being yanked around the sun by some mysterious, invisible string. Instead, the sun is incredibly massive, so it creates a huge dent in the fabric of space-time, like our bowling ball. Earth, being much smaller, is like a marble rolling along the edge of that giant curve created by the sun. That's its orbit. Earth is just following the path of least resistance through the bent space-time around the sun. And it doesn't stop there. Earth itself has mass, so it creates its own smaller dent in space-time, and the moon. It's just rolling along the curve created by the Earth. It's all about objects following the curves made by other, more massive objects. No mysterious pulling forces, no invisible strings, just geometry. So let's go back to the beginning. When I hold this ball and let it go, what's actually happening according to Einstein? It's not being pulled down in the old-school Newtonian sense. Instead, the ball is simply following a path through the space-time that has been curved by the massive object right beneath it, the Earth. And because the Earth is so incredibly massive, that curve in space-time is directed straight towards its center. So the ball follows that curve, which we perceive as it falling straight down to the ground. It's the most natural path it can take. Let's do a quick recap to make sure it all clicks. First, we have Newton's idea. Mass attracts other mass with a pulling force. The more mass, the stronger the pull. The closer you are, the stronger the pull. It's a great and useful description. Then we have Einstein's deeper explanation. Mass doesn't pull, it bends space-time. Other objects then follow these curves in space-time. The more mass an object has, the more it bends space-time, and the stronger its gravity appears to be. So there you have it, gravity in a nutshell. It's one of the fundamental forces that shapes our entire universe, from a falling apple to the dance of entire galaxies. And the deepest rabbit hole of all involves what happens when space-time is bent to its absolute limit. I'm talking about black holes, the ultimate space-time benders. If you want a deeper dive into those cosmic monsters, make sure you're subscribed to the channel because that episode is coming very soon. Thanks for watching.